Hi everyone, this is Dr. Nak, and today we're going to talk about domain and range. In last section, we did talk about a little bit of domain and a range given an ordered pair. Meaning, if you're given x comma y, then we said that x belongs in the domain, and the y is the element of the range. Okay. So we're going to talk about the domain and a range, but it's no longer an ordered pair now. We're going to be talking about the domain and a range of functions. So just to save some time, I've already written down the notes. So let's just go over this real quick. Okay, so here it is. How to find the domain of a function. So step 1, identify the input values. Step 2, identify any restrictions on the input and exclude those values from the domain. Step 3, write the domain in interval and set builder notations. Now, if you're not familiar with interval and set builder notations, I made the separate video on that, so please watch that. And of course, please let me know if you have any questions on that. All right, so let's take a look at this one. I pretty much summarized everything for you here. So how to find the restrictions? Because given a function, right, we're going to have to find the restrictions on that function. Now, if there is a restriction, then we have to throw those values away to find the domain. So in this class, we're given 3 cases. So first case is a polynomial. Second case is a root function. And the last one is called the rational function. Rational function means that you have a polynomial over a polynomial. Okay, so those are the 3 cases that we're going to be talking about today. Okay, so let's first go with case 1. Suppose you're given f of x to be a polynomial. So now those of you who forgot what the polynomial looks like, it looks something like this. So f of x equals 3x to the 5th plus 4x squared plus 1. And in this case, this is a 5th degree polynomial. You can also have something like this. F of x equals to just like maybe a constant 5. This is still a polynomial of degree 0. Okay, so what is not a polynomial, right? So one of the examples of not being a polynomial, it all depends on the exponents here. Okay, so this exponents on the variable has to be a positive whole numbers. So if you have something like, let me see, let's go with like a g of x equals to 3x to the negative 5 plus 4x squared, let's just say. So this is no longer a polynomial because of the exponent on the variable is negative. Okay, so in order to be a polynomial, all the exponents on the variable has to be 0, 1, 2, 3, 4, and so forth. Okay, now let's talk about the domain of the polynomials. Okay, so domain of f, so no matter what it is, no matter what kind of polynomial that you're given, as long as if it's a polynomial, domain is going to be the all real numbers, meaning you can plug it in any value of x. Your x can be a positive number, negative numbers, irrational number, or fractions, decimals. You can plug it in any numbers in f, and your output is always going to be defined. And how do you write that in set builder notation? Oh, by the way, when I say set notation, I mean set builder notation. You'll write it like this. So we read this as settable x. This bar means such that x is all real numbers. So make sure to put a little curly bracket. Let's just read this together again. We say that this is settable x values such that x is all real numbers. All right, so that's called a set notation. Now the interval notation, since you're trying to describe all real numbers, so the interval notation is going to be from negative infinity to infinity. Now, do not put a closed bracket around the infinity. Infinity and negative infinity, you're always going to have open parentheses. Okay, so if it's a polynomial, it's easy peasy. No matter what, your answer is going to be all real numbers. Okay, so now let's go with case 2. So suppose you're given the nth root of u, where u is still going to be a function of x. Okay, so now n can assume either even or odd numbers, correct? Because if it's a square root, then our little n here is 2, but we just don't write that. Okay, and then our n could be 3. So in this case, if that's the case, we read it as cube root of something. And if n is 4, then we just call it the fourth root of something. So again, the root function is going to be different whether n is even or odd. Okay, so let's first go with the when n is even. Examples, square root, fourth root, sixth root, and so forth. Okay, so the domain of f is going to be a settable u such that u better be greater or equal to 0. Now, u is the one that sits underneath the root sign. Now, let's recall that if you had a square root, let's just talk about the square root. If you're given the square root, do you remember that whatever you put inside has to be 0 or greater or equal to 0, right? Meaning square root of a negative number, we get an imaginary answer, so we don't want to go there. Okay, so for that reason, if n is even, then whoever sits inside of the root has to be greater or equal to 0. All right, so here it is. Now, let's go with n is odd. So meaning this is going to be a cube root, fifth root, and so forth. In this case, we got a super duper easy answer. Our answer is going to be the domain of f is set of all real numbers again. Meaning, if you're given the odd root, like a cube root, fifth root, you can plug it in any number that you want inside of the radical. All right, so that was case 2. And let's go with case 3, rational function. All right, so think of this as being a fractions, right? So do you remember the restriction of fractions? Right, the denominator cannot be 0. I don't know if you remember that or not, but same thing applies for the rational function. So if you're given the polynomial over the polynomial, right, you have to exclude the values where the denominator goes to 0. All right, so the domain of f is set of all x values such that the denominator does not equal to 0. Don't worry, we're going to do some examples in a minute. Oh, and then if you're still wondering what does it mean to be a rational function, here's a little example. Make sure the top is a polynomial. Top is a polynomial, yes, because exponent on the variable is a positive whole number. And on the numerator, right? I'm sorry, this is the denominator. Denominator is also a polynomial of degree 1. So if you have a polynomial over the polynomial, and that's called the rational function. All right, so let's take a look at example 1. Find the domain of the function in interval and set builder notations. Okay, so let's first go with part A. We got f of x equals negative 3x times the quantity x plus 1 times by the quantity x minus 2. Now, do you all see that if I multiply everything out, do you see that we're going to have a polynomial no matter what? So if you don't believe it, then let me just multiply this out. So you got negative 3x, and then I'm going to FOIL. So you're going to have x squared minus 2x plus x, and then minus 2. So that's same thing as negative 3x. And then you got, what do we get here? X squared, and then minus x, and then minus the 2. So do you see that we're going to have negative 3x cubed plus 3x squared, and then plus 6x. So notice that this is a polynomial. Now, so therefore, no matter what, our domain of f, so I'm just going to write it as therefore, remember the 3 dots means therefore, domain of f is a set of all x values such that x is all real numbers. All right, so this is your set builder notation. So I'm just going to write it as set notation for short. Now, for the interval notation to express all real numbers is going to be open negative infinity, comma, to positive infinity. All right, so that's going to be our answer. So let me just box that. Okay, so again, the bottom one is called the interval notation. All right, let's look at part B. G of x equals negative 5 minus the square root of 6 minus 3x. Now, since we're given the eventh root, let me just write this out. The restriction is that whoever sits inside of the eventh root has to be greater or equal to 0. All right, so pretend this is your u, because this is the quantity that sits inside of the radical. So the restriction is going to be 6 minus 3x better always be greater or equal to 0. Now, if you set that one up, all you have to do is solve for x from here. So let's do it. You subtract negative 6, so you're going to have negative 3x is greater or equal to negative 6. Now be careful on the next step. In order to solve for x, you're going to have to divide it by negative. Do you remember what happens to the inequality if you have to divide by the negative? Yes, you have to swap your inequality sign. So in this case, we're going to have x is less than or equal to positive 2. All right, so let me just box that. This is not our official answer, but I'm just going to box it. Now let's write down our set notation and then the interval notation. So our set notation, let me write set interval. Okay, for the set domain of f, all right, here we go. This is how you write it. Settable x values such that, and then all you have to do is insert what I just boxed in red. X is less than or equal to 2. All right, so that's the set notation. Now, those of you who cannot visualize the interval notation immediately, draw a number line. Okay, so suppose this is my number line. Here's negative infinity to infinity, and suppose this is 2. So then we're going to have to express the interval notation such that x better be less than or equal to 2. Okay, so where is that? X is less than or equal to 2 will be this region here. Okay, so that means what? We're going to have to start from negative infinity, and then you have to end at 2, but 2 is included, so you put a bracket around it. All right, so in this case, our interval notation is going to be open negative infinity, comma, 2, close bracket. Once again, on the infinity or negative infinity side, you better have open parentheses, no matter what. All right, so here it is. This is going to be our answer. Now let's look at part C. H of x equals negative 5 minus the cube root of 6 minus 3x. So this is same thing as part B, but instead of square root, I just put down a cube root instead. Now, since this is cube root, are there any restrictions? Answer is no. Remember, if it's an odd root, your answer is always going to be all real numbers no matter what. Meaning you can plug it in any number in place of x, and then you should still be able to compute cube root of that number. Okay, so in this case, there is no restrictions. So odd root implies no restrictions. So then our answer is going to be, so our set notation, so this is interval. So again, our set notation for the domain of f is settable x such that x is all real numbers. And then interval notation of the domain of f, I don't know why I rewrote domain of f, but that's okay. So this is going to be open infinity, negative infinity to positive infinity open. And that's going to be our answer. So I'm going to box this. All right. So once again, this is telling you that no matter what value of x that you're going to plug it in here, cube root of that number is still defined. Whereas in part B, remember the domain of f is settable x such that x is less than or equal to 2, which means that our square root is defined for all the values that are less than or equal to 2. So suppose if you put something that's bigger than 2, right? So let's just say 3. Okay, let's see what's going to happen. All right, so remember, 3 is outside of the domain, correct? So if I plugged it in 3 in here in place of x, you're going to have the square root of 6 minus 9, which is going to give us a negative radicand. So in that case, remember, the square root of a negative is undefined. Okay, so in order for the square root to be defined is that all the value that you're going to plug it in for x has to be less than or equal to 2. And that's what you just discovered. All right, so now let's take a look at something a little bit different. Okay, so we're still playing the same game. We want to find the domain. So part D, p of x equals 5 over 2x plus 1. Okay, so again, 5 is a polynomial. In fact, that's a polynomial of degree 0. And 2x plus 1 is also a polynomial of degree 1. So we have a rational functions going on here. All right, so remember the rule for the rational function. Rule means restriction. So let me write restriction is that the denominator cannot go to 0. So the restriction is going to be 2x plus 1 cannot be 0. And then from there, all you have to do is just solve for x. So you're going to have 2x does not equal to negative 1. So x does not equal to negative 1/2. So this is the only restriction that you're going to get. All right. So in order for us to write this in the set builder notation, let me just write set in an interval. But before I write down the set notation, let's make sure that you're understanding what you're computing here. So the restriction is that x cannot be negative 1/2, right? So that means what? If I plugged it in negative 1/2 in place of x, do you see that we're going to have 2 times negative 1/2, which is negative 1, and then plus 1, which is going to give us a 0. So we got a 0 on the denominators, and that cannot happen, right? So that's what you just computed. So you can plug it in any other number for x. Your denominator will not go to 0. Okay, so the only problem point is at negative 1/2. All right, so let's write down the set notation. So the domain of P is settable x values such that x is all real numbers, but x cannot be negative 1/2. All right. Now let's go with the interval notation. So draw yourself a number line if you want. So here's negative infinity to infinity. Here's my problem point, which is negative 1/2. Now, x cannot be negative 1/2, but any other x's, it's safe, right? So I'm going to put an open parentheses around negative 1/2, and then I'm going to shade everywhere else. Now, the shaded area is going to become the domain of P. Okay, so just translate this situation directly below. So what do we got? So this is shaded area is going to be from negative infinity to negative 1/2. Be careful here. This better be open parentheses. And then another open parentheses from negative 1/2 to positive infinity. Now, notice that we have 2 intervals going on to express the domain of P. So in this case, you're going to union these 2 together. So in order to write it properly, please put a little u in between. Okay, so our interval notation for the domain of P is going to be from negative infinity to negative 1/2 open union with negative 1/2 to positive infinity. So this is going to be our answer. Alrighty, so now let's try part E. So we're giving q of x equals x minus 3 all over x squared plus 9x minus the 22. So again, top is a polynomial of degree 1 and the bottom is a polynomial of degree 2. So we're talking about a rational function. Now, what is the restriction? Let me just write. Okay, so the restriction is that the denominator cannot go to 0. So I'm going to write it as x squared plus 9x minus 22. This guy cannot be 0 because if it's a 0, we're going to have a 0 in the denominator, which makes q of x undefined. All right, so now what we need to do is we got to find those value of x. So guess what we need to do? Yup, we got to factor. I'm not quite sure how you learn to factor, but either way you want to do it. Let me just write, cannot be 0. You better have an x and an x. One sign better be positive, negative. So what if I put 11 and a 2? Would that work? So if I check, then you're going to have x squared. I'm multiplying these out. So x squared, and then you got minus 2x plus 11x, and then minus 22, so which is going to give us x squared, and then plus 9x minus 22. Right, it matches up. So that should be the factor form. No matter which way you learn to factor, your answer should be that. All right, so now from here it's easy peasy. So if I have x plus 11 times by x minus 2 does not equal to 0, that means that x plus 11 cannot be 0. And x minus 2 cannot be 0. All right, so that means what? X cannot be negative 11 and x cannot be 2. Oh, look at that. We got two restrictions going on now. Okay, so let me just box that because this is important information. So let's see what's going to happen if I plugged it in negative 11 in place of x. Okay, so if I plugged it in negative 11 in place of x, let me just change the color here. What do we get? You're going to have, when x is negative 11, then you're going to have negative 11 squared plus 9 times negative 11, and then minus the 22. Now, negative 11 squared becomes positive 121, and then minus, we're going to get 99, and then minus the 22. So, which is going to give us 22. Minus the 22, which is going to give us a 0. Okay, so notice that what we just did was, what we just checked, I should say, is that when x is negative 11, then denominator is going to go to 0. So that's a problem. Okay, so therefore x cannot be negative 11, meaning for the domain of Q, you have to exclude negative 11. Now, same thing's going to happen here if you plugged it in 2 in place of x. So, you know what the heck, let's just check. Okay, so when x is 2, let me just put a bar here, then you're going to have 2 squared and then plus 9 times 2 minus the 22, which is same thing as 4 plus 18 minus the 22, which is same thing as 22 minus the 22, which is going to give us a 0. Okay, so our answer is correct. So now let's write down our answer. Okay, so let's write it as set and then the interval. Okay, so let's first go with the set notation. So for the domain of Q is set of all x values such that x is all real numbers, except that x cannot be negative 11 and x cannot be 2. All right, now let's go with the interval notation. So again, let's just draw a picture to see what's going on. Oh my gosh. So here is negative infinity to infinity, and negative 11 is less, so that would be the left-hand side of 2. So here we go. All right, so now x cannot be negative 11, which means I'm going to have an open circle, and also x cannot be 2. So I'm going to have another open circle around 2, but I get the shade everywhere else. All right, so just translate it right below. So what do we got going on? We have negative infinity to negative 11 open, and then you have negative 11 to 2 open, and then you have a 2 to positive infinity. Okay, so since we have more than 2 intervals going on, please connect them with the union sign. All right, so that's the domain of Q in interval notation. So let me just box that for the answer. So this is such a big answer for me to box. All right, here we go. All right. Now let's look at part F. Our f of x is 3x minus 1 over the square root of 5x plus 1. Now, this is no longer a rational function. Do you see why? Top is cool. Top is a polynomial of degree 1, but the bottom, if you have a square root, it's no longer a polynomial now. But it's all right. We got this. Treat this as a fraction, right? So our restriction is still going to be the bottom cannot go to 0. All right, so let me write that out. So the restriction is that the square root of 5x plus 1 cannot be 0. And then you have to be careful here. You got two restrictions, different restrictions going on in this problem. So first, you're going to have to look at the whole entire denominator and make sure that does not go to 0. And since you're given the square root, what was the restriction on the square root? Whoever sits inside of it has to be always greater or equal to 0, correct? So we got two different types of restrictions. One of them is the bottom cannot go to 0. And the second one is whoever sits inside the square root has to be always greater or equal to 0. All right, so let's take one thing at a time. Okay, so let's go with the circle one first. So in order for us to solve for x, I need to square both sides. So here you're going to have 5x plus 1 squared. That's not equal to 0 squared, which is going to be 0. So that implies that we're going to have 5x cannot be negative 1. So that implies that our x cannot be negative 1 over 5. So this is one restriction. All right. And then the second restriction, this one isn't so bad. So you got subtract 1 from both sides. Then you're going to have 5x is greater or equal to negative 1. So our x is greater or equal to negative 1/5. All right. So now let's just take a look at this. Okay, so you have to look at these two things here together. So what's going on here? This is telling us that, let me just read the bottom one, x has to be greater or equal to negative 1/5, and x cannot be negative 1/5. So guess what? You're going to have to get rid of this. If I combine these two answers together, right, do you see that I have to write as x is strictly greater than negative 1/5? Do you see that? So let me just go over it again. So here, x cannot be negative 1/5. But here, you're saying x is strictly greater than negative 1/5 or equal to negative 1/5, right? So that means that you're going to have to get rid of this equal to sign now. Okay, so if I omit that, then what do we get? X is just strictly greater than negative 1/5. Okay, so this is going to be the answer if you combine the two restrictions together. All right, so now let's go with the set notation, set builder notation. So let me see, the domain of f. Set of all x such that x is all real numbers, of course, so x is strictly greater than negative 1/5. All right. Now, in order to do the interval notation, again, just draw yourself a number line if you feel more comfortable doing it that way. So here's negative 1/5. X has to be strictly greater than negative 1/5. So you're going to have an open parentheses here, strictly greater than. So this is the region that we get the shade. So to translate it directly below, you're going to have negative 1/5. Around that is the open parentheses, and then positive infinity, and then open parentheses. So in this case, this is the domain of f in interval notation. All right, so let me just box this for the answer. How you all doing? I hope you're getting it. All right, so let's do maybe one more or so. And I just lied to you. Let's do two more. Why not? Okay, so let's go with part G. So we got g of x to be 3x over to 3x. All right, so yes, I know. It's so tempting, right? 3x over to 3x, that's going to go to 1, correct? Because you can cancel 3 goes into 3 once and x goes into x once. Okay, but in order to find the domain, do not cancel out and then simplify the function. Okay, you're just going to have to take the function as is to compute the domain. So here, we're given a first degree polynomial with a first degree polynomial. So this is a rational function. Okay, so you're going to have to treat it like that. All right, so then our restriction in that case is that the denominator cannot be 0, correct? So in this case, our denominator is 3x cannot be 0. So dividing by 3 on both sides, you're going to have x cannot be 0 over 3, which is same thing as 0. So let me just write that out as x cannot be 0. Now, if you simplify this, right? Let's just do it in the wrong way. Okay, so if I simplify this, yes, I know this is going to go to, so this equals to 1. But the thing is, 1 is a polynomial of degree 0. So which means that the domain of G, you would say the domain of G is all real numbers. But that was not the case, wasn't it? Because we have a restriction saying that x cannot be 0. So in order for you to find the domain of a function, right? Domain of a rational function, let's just say, compute the domain first before you simplify it. Okay, so in this case, let me just write it out. So here is the set builder notation, and here's the interval. So the domain of G is settable x values such that x is all real numbers and x cannot be 0. So if you want to, you don't have to write x is all real numbers. You can just write it as x does not equal to 0. This is fine with me. All right, so then on the interval notation, then what do we get? Negative infinity to 0, open, and then union, 0 to positive infinity. Okay, so here is our answer. All right, and this is the reason why I decided to do 2 more examples, not just 1. All right, so now let's look at h of x. Part h, which is h of x, equals x squared minus 9x over x squared minus the 81. Now, why don't you try this problem on your own? So please pause the video right now and try it. Why am I pausing? Okay, so I'm going to pretend that you tried it already. So let's do it. So first thing first, right? This is a polynomial over the polynomial. So the restriction is that the bottom cannot be 0. Let me just write it a little bit down below. All right, so the bottom cannot be 0 means x squared minus 81 cannot be 0. Now, we're going to have to factor this, or you can, add by 81 on both sides, but I don't know which way you want to do it. Whichever is okay. So you're going to have xx plus 9 and then minus 9 cannot be 0. So in this case, x cannot be negative 9 and x cannot be 9. So these two values are the restriction for that polynomial of h of x. Okay, now let me try this. I could still simplify h of x, right? So suppose I did that. Okay, so then let's see what's going to happen. So I'm just going to write it like this. So you can factor the x out from the top. So you're going to have x minus 9. On the bottom is x plus 9, x minus 9. Oops, x minus 9. And then look at it. I can cancel out the x minus 9. And then our simplified version of h of x is nothing but x over x plus 9. So if you first simplified it, right, then only restriction that you can get out of it is when x plus 9 does not equal to 0. Correct? So that only will give you x cannot be negative 9. But look at it. Our domain is not just that. X also cannot be 9. Okay, so again, in order for you to compute the domain, just do not simplify. All right, so that's the lesson that we've learned. Okay, so now let's write this our answer then. So our set notation and then our interval notation. Okay, so our set notation for the domain of H is settable x values such that x is all real numbers, but x cannot be -9, and then x cannot be 9. All right, now if you're not comfortable writing the interval notation, just draw the situation out again. So here's -9 and 9, open, open, and then shade everywhere else. And just translate it below. So this is same thing as -infinity to -9 open, union -9 to 9, union, and then 9 to positive infinity. So this is going to be our answer. All right, here we go. How are you all doing up to here? I hope you're getting a little bit more comfortable computing the domain. Please let me know if you have any questions, okay? All right. Now what we're going to do is this. We just find the domain of the functions. Now what we're going to do is we're going to find the domain and a range by looking at graphs. I think best way to learn this is by examples, so let's do it. So example 2, find the domain and a range, part A. Boom, there is the graph. In fact, that's the graph of x cubed plus 1. Okay, so now remember the domain is settable x values where the function's defined. All right, and the range is settable y values where the function's defined. Also, please note that, do you see those like a little arrow? That means that your graph's going to keep going, in this case, going to keep going up, 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 and then here this is going to go towards downwards. All right, let's first try to find out the domain of this function. Okay, so again, domain is where the function's defined. So let's just say when x is 2, is my function there? Yes. Now when x equals to 5, is my function's going to be there? Answer is yes, because here's my x equals to 5. Now, eventually, if I keep doing this, your graph, remember this tail end is going to keep going upward. Okay, so here, yes, eventually, where at x equals to 5, your function will be defined. Now, we could do the similar thing towards the negative x values. When x equals to -4, is my function defined? Yes. When x equals to -7, is my function defined? Yes. It will be, but maybe like over here somewhere, then graph can touch it, right? So in this case, our domain is going to be all real numbers. Let me just shade all the value of x where the function's defined. So that will be that whole entire line, right? No matter what x values that you're going to pick, on that line, your function will be defined. So let's write our answer. So the domain of f is settable x such that x is all real numbers. All right, and this is same thing in interval notation from -infinity to infinity. All right, now let's talk about the range. Range is where the y values where the function's defined, right? So in this case, you'll probably see it much easier than the domain because look, now you have to look at all the set of y values. Okay, so let me just put down the arrow. So remember, all the numbers on the y values are on this line, right? Vertical line. So here, when y is 2, is my function there? Yes. When y is 5, is my function's going to be there? Yes. When y is 8, is my function's going to be there? Yes. When y goes all the way up to 1,000, is my function, is it going to be there? Yes. Right? So let me just shade down the region where the function's defined in terms of y. That would be, let me just draw a line on the side so it doesn't overlap. So from here all the way down to here. Right? In fact, let me just keep writing the arrow here. So on this one, I should have written the arrow. Okay, so again, in this case, our range is going to be all real numbers again. So let me write this as the range of f is also settable x such that x is all real numbers. And interval notation is negative infinity to infinity. Okay, so let's try something a little bit different. So let's go with part B. So let's find the domain. Okay, so domain is again set of all x values where the function is defined. Okay, so let's go with when x equals, what is that, 1, 2, 3? When x equals to 3 is the function defined? Yes. X equals to 15 is my function defined? Yes. But what about, well, let's go with when x is 0, is my function defined? Yes. In fact, your graph starts at x equals to 0. Now, what about when x equals to negative 2? Is my function defined there? No, there is no function, right? So that means that your domain has to start from 0 and all the way up to infinity. Okay, so how do I write that is this. So, let me just do the same thing as what we did earlier. Let me just shade the region where the domain is. Okay, so in this case, let me just write the domain of f is settable x such that x is greater or equal to 0. And that in an interval notation is closed 0 because 0 is included. 0 is defined at x equals to 0 and all the way up to infinity. Okay, now let's try to find the range. Okay, so the range is settable y values where the function is defined, right? Okay, so what about at negative 5? Y equals to negative 5. Let's just go over here. Is my function there? No. So where does the function begin along the y-axis? Well, y has to start from 0, correct? So here, and then remember this tail end is going to keep going and going and going upward, right? So eventually this is going to go towards infinity. So eventually your function would be defined from when y equals to 0 all the way up to when y equals to infinity. So let me shade those regions again. So it's going to start from y equals to 0 and it's going to go all the way up to infinity. All right, so our range is going to be settable. Be careful here. Uh-oh, I made a mistake. Do you see why? Range is settable y values, right? So my apologies. Look at what I did here. I put x. This should be a y. All right, so let me fix that. Sorry about that. There you go. That's much better. All right, so again, range of f is settable y values such that y has to be greater or equal to 0. So again, on the interval notation, this is going to go close 0 all the way up to infinity. All right, let's look at part C. So our function is f of x equals 1 over x minus 2. Now, I don't know if you can see that in the picture or not. There is this thing called the vertical asymptote at x equals to negative 2. Is that right? 1, 2. Yeah, this is negative 2. So there is this asymptote, which means that the tail end of the graph will get really, really, really close to the vertical asymptote, but it will never going to touch that vertical asymptote. Okay, now same thing along the y-axis. We have a horizontal asymptote. I don't know if you can see these dots right here. So again, our tail end of the graph, so tail end, this tail end and this tail end will get really, 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 really close to this axis here, which is y equals to 0, but it's never going to touch it. Okay, so with that said, let's find the domain. So let's start from the negative infinity side. So is my function, is it going to be defined there When x equals to maybe negative 10, answer is yes, because again, remember, here's the horizontal asymptote, and then this graph's going to keep going and going and going and going, but it'll never touch the asymptote. So in fact, your domain is going to start from negative infinity, right? Let me just draw that line again. Can you see that okay? You're going to have from negative infinity all the way up to when x is close to x equals to negative 2. But remember, at negative 2, there is a vertical asymptote, which means that your graph is never going to touch it. Okay, so with that said, I better have a hole here at when x equals to 2. All right, so let me just write the arrow. Okay, so that's the domain part 1. Now let's go with the towards the positive, and the graph that's in the quadrant 1. Okay, so where is the graph starting? So let's see. Our tail end here, it's never going to touch y, this is x equals to negative 2. Okay, so here still when x is really, really, really close to negative 2, your function's going to be defined there, except that when x equals to negative 2, remember this tail end of the graph is not going to touch it. So you still have to eliminate x equals to negative 2. But what about the rest of it? Is my function defined for all the rest of the x values? Answer is yes. So if I have to draw a line through it again, so your domain's going to be, so let me just shift it over here. I don't know, can you see this okay? I'll just write it here. All right, so your domain looks like from negative infinity to negative 2, but you have to exclude the negative 2, right? Because negative infinity to negative 2, and then from negative 2 all the way up to infinity. That's where your graph is defined, the function is defined. Okay, so with that said, let's write down our answer. So the domain of f, set of all x values such that x is all real numbers, but x just cannot be negative 2. Okay, so how do you write that in an interval notation? Would be negative infinity to negative 2 open, union to negative 2 to positive infinity. All right, now we're going to play the same game with the range. Okay, so the range is set of all y values where the function's defined. So where's my y value defined? Remember, you're looking along the y-axis now. So again, this tail end here is never going to touch the axis, the horizontal axis. So that means that your graph, if I look at it this way, your graph is going to start from when y equals to 0, but 0 has to be excluded because this tail end is never going to touch this horizontal axis of y equals to 0. Okay, so let me just jot that out. So I'm going to have an open from here. Now, what about the rest of it? Is it defined all the way above? Yes. So from here, your range, you can go all the way up. And then same thing for the graph that's in the third quadrant. The only part that this is not going to touch is at the y equals to 0. But for the rest of it, your function is going to be defined. Okay, so here, what I'll do is I'm just going to go from here all the way down to here. And then just put an arrow. Okay, so let's translate that then. So what is our range is going to be? Okay, so our range is going to be set of all y values such that the only problem point, right? Look at this green line here. They're all real numbers except for when y is 0. Then we have a problem because your graph is never going to touch y equals to 0, right? So all you have to do is set of all y such that y is all real numbers, but y cannot be 0. All right. So in terms of an interval notation, that's going to be negative infinity to 0 open, union, and then open 0 to positive infinity. All right, so let's try a few more. Again, practice makes perfect, right? So now let's look at some of the funky ones. Okay, so let's go with part D. So that actual graph is absolute value of x plus 1, but look at it. We got the restricted domain going on. All the graph is defined from x is less than or equal to 2. Right? Because your graph keeps on going towards this end, but your graph is going to stop right here. All right? So with that said, let's first find the domain. You know what? Why don't you pause the video and find the domain and a range for this graph? All right, so I'm going to pretend that you tried it. So let's go with the domain. So what did you all get? Okay, so I'm just going to go like this. Your graph is defined from x equals to 2 and then towards the negative infinity, right? So I think this is correct. Okay, this one includes 2. All right, so our answer for the domain of f is settable x such that x is less than or equal to 2. And also, in an interval notation, is going to have negative infinity to 2 closed. All right, so that's the domain. Now let's go with the range. So did you try the range? What did you all get? Okay, so let's see. Your graph, where's the lowest tip of the graph, right? If you're going to compute the range, right, you want to look at the graph bottom upward. And then if you go bottom upward, where's the starting y point? It looks like it's going to start from y equals to 1. And then it's going to keep going towards infinity. Right, so let me do the same thing as what we did before. I'm going to draw the line where the function's defined along the in terms of the y values. So if I do that, then it's gonna start from here, right, and it's gonna go all the way up like that. Okay, and then yes, your function is in fact defined at the x, the y equals to 1. So this point right here should be included. Okay, so with that said, how do I write that? So our range of f is settable y values such that all the y values has to be greater or equal to 1. Okay, so in an interval notation, you're going to have close bracket 1 all the way up to infinity. Okay, so that's the answer. How did you all do on this one? I hope you did okay. All right, so now let's take a look at the next one, another funky one. Okay, so what do we got going on? So we have f of x equals to 4, right? But the thing is, this graph is only defined from -2 to 5, but -2 is excluded. Maybe I shouldn't have written that already, because that's actually going to be the domain, as you'll see. So for the domain, this is pretty straightforward, I think. So our domain of f, in this case, is going to be from where to where? From, what is this? 2? Oh, why did I put a dot there? That should be open. And then all the way up to 5 included, right? But your graph stopped here. So the domain of f is settable x such that x is between 2 and a 5, but 2 is excluded. So you're going to have 2 less than x or less than or equal to 5. All right, so in an interval notation, this is going to be, let me see, open 2, comma, 5 closed. All right, so that's the domain. Now let's talk about the range of f. Okay, so again, you're looking along the y-axis now. So if I look at along the y-axis, right, where is this function defined? I'm talking about the y, not the x now. It's only defined at y equals to 4, isn't it? So in this case, I cannot generate any line, but I'll just dot it. So this is just y equals to 4, right? So in this case, our range of f is settable y values such that your y has to be exactly equal to 4. Does that make sense? Because look, if I play the same game here, right? Along this vertical line, is my do I have a function at when x equals to 3? No, there is no function here, right? But x equals to 5, is my function there? No, but yes, my function's only there when y equals to 4. So that's the reason why our range is y equals to 4. All right, so let's do one more. Part F. Okay, so again, pause the video and try to find the domain and a range on your own. Okay, I'm gonna think that you did this problem, so let's do it. Okay, so let's go with the domain, right? So domain, it looks like it's gonna start from here. That should be an open circle, and then it's gonna go to, remember the tail end keeps going and going, so eventually it's gonna go towards the negative infinity. Right, so it looks like our domain is going to be domain of f is settable x values such that all the x values has to be strictly less than 1. Sorry to spoil your fun, I already wrote that out, huh? Okay, so now let's go with the range. What did you all get for the range? All right, I'm just going to write settable y such that. Okay, so where's my function defined? Where does the graph start? From bottom upward. Well, when graph starts from y equals to 0, and then it's going to keep going all the way up to positive infinity, correct? So in this case, if I have to draw that the line, we're going to have, close it here, and then all the way up, just like that. And this point right here is included. Y equals to 0 is included. All right, so with that said, our range is going to be settable y values such that y has to be greater or equal to 0. All right, so in this case, how do we write that? Is close 0 all the way up to positive infinity. Oh my goodness, are you all burnt out yet? I'm getting kind of burnt out, but let's hang in there together, all right? So there's one more little topic that we need to talk about. So here is the last topic in this section. We're going to be talking about this thing called the piecewise functions. So what is the difference between the regular function and piecewise function? Well, before you're only given f of x to be either x squared or f of x to be 3. Now, piecewise means your f of x has more than one functions, but that function is only defined on the restricted domain. All right, so how to graph the piecewise function? So step 1, indicate on the x-axis the boundaries defined by the intervals on each piece of the domain. Step 2, for each piece of the domain, graph on that interval. Now, do not graph two functions over one interval. So don't worry, I will explain everything in a minute. All right, so let's look at example 3. So here is our piecewise function. F of x is x squared when only on the region where x is less than or equal to 1. F of x equals to 3 only between when x is 1 and 2. Sorry, x is between 1 and 2, I should say. And then f of x equals to x for all x that's greater than 2. Okay, so let me just, chop up the interval accordingly. Okay, so if I chop up the interval, let me see. All the x values that's less than 1, all right, so here is that. And then let's go with the domain is 1 to 2 when 1's not included. So that will be 1 all the way up to 2. Oh my gosh, this is so little. Can you see that okay? Oh my goodness. So I have open parentheses around x equals to 1, and I got a closed bracket going on what is that? X is 2. So it's going to be in this region here. Okay, now x is strictly greater than 2, so that will be starting from 2, these regions. All right, so according to each domain, your function is going to be different. Okay, so let's first go with f of x equals to x squared. So if you don't know what the graph looks like, you can always make a chart. Okay, so let's go with x and then y equals to x squared. Okay, now remember, you only want to draw the graph on that the certain interval. Okay, so where is the interval defined from where to where? From negative infinity all the way up to when x is, where is that? X is 1. So I'm just going to go with when x is 1, x is 1, and then I'm going to go x is 0, negative 1, negative 2, and negative 3, and so forth. All right, so let's go. When x is 1, you're going to have 1 squared, which is 1. And then when x is 0, you're going to have 0 squared, which is 0. And then you're going to have negative 1 squared, which is 1. Negative 2 squared is 4. Negative 3 squared is 9. Okay, so let me just jot down these points, 1, 1, 0, 0, and I'm going to connect the dots. Negative 1, 1, negative 2, 4, and then negative 3, 9. All right, so 1, 1 will be here, and then 0, 0, negative 1 and 1, negative 2 and a 4, negative 3 and a 9. So it looks like our function is gonna look like this. Oh my gosh, pretend, here, I'll just make the dot fat, there you go. Okay, pretend that's touching when y equals to 9, please. So it's gonna keep going. All right, so that's the graph of that. Now let's look at that tiny, tiny itty bitty interval from 1 to 2. So that's nothing but y equals to 3, correct? So that's basically telling you is this. So if I have to do the same thing, x and a y, so where's the x values that's starting from? Well, gonna start from 1, but a 1's not included. All right, but when x is 1, your y is gonna be 3, right? Because y equals to 3 no matter what the x value is. And when x equals to 2, your y is still gonna be 3. Okay, so y equals to 3, where are you? That's y equals to 3 is here. Okay, so it looks like our graph is going to be open, and then all the way here, it's a constant function, and then I'm going to close the dot here. All right, so that's sorry you guys, it's so tiny, but hopefully you can see that. So that's the graph of y equals to 3 on the interval 1 to 2. All right, so now let's go with the last graph, which is y equals to x. So I'm going to make the chart. Okay, so where is the graph supposed to begin? When 1, 2, 3, when x is 2, it's going to start, right? Although this is excluded. Okay, so I'm going to put a star here. So 2, and then let's go with 3, 4, 5. I think that's enough. Okay, so now your x and y values are going to be the same. Okay, So when x is 2, our y is 2. So you're going to have open dot here. Is that y equals to 2? Yeah, it is, right? Okay. And then 3, 3. 4, 4. 5, 5. So you're going to have a straight line here. Okay, so let me connect those dots. All right, so that's the graph of y equals to x. So let me just write y equals to x. And then this itty bitty one is y equals to 3. And then this one is y equals to x squared. Now all together, that's the graph of our f of x. Okay, so that was part A, and we still have to do part B. We want to find f of negative 1, f of 1, f of 1.5, f of 3, and f of 2. All right, so let's first go with f of negative 1. That's basically telling you when x is negative 1, what is the corresponding y value? All right, so let's take a look. When x is negative 1, what's the corresponding y value? Y is positive 1, so therefore f of negative 1 is 1. So I'm just going to write that right above here. All right. Now let's go with the next one, f of 1. So where's x equals to 1? What is the corresponding y value? Your y value is going to be 1 as well. So here I'm just going to write it as 1. Now let's go with f of 1.5. Why did I do that? This tiny interval here. Sorry, y'all. So 1.5 is dead center of this orange interval. So what's the corresponding y value? Your y is 3. Okay, so I'm just going to write that as f of 1.5 is 3. Now let's go with f of 3. When x equals to 3, got 1, 2, 3. Okay, we're looking over here. When x is 3, what is the corresponding y value? Looks like 3. So therefore, f of 3 is going to be just 3. Okay, let's go with f of 2. Okay, so when x equals to 2, so here's 1, here's 2, right? Sorry about this small grid, you guys. Okay, so when x equals to negative 2, we have two dots, right? One of them is the open dot, one of them is the closed dot. So in this case, remember, open dot means your function is not there. Closed dot means, yes, your function is there. Okay, so at x equals to negative 2, the only function that's defined is at y equals to 3, not y equals to 2. All right, so with that said, our f of 2 is going to be just 3. All right, so now let's take a look at this. Okay, so we want to graph the piecewise function. All right, so let's do our last example. We can do it. You can do it. Okay, so we're going to play the same game, but our f of x is different. That's all. Okay, so if you want to try this on your own, go for it. Just, stop the video and then just try it on your own. Okay, but meanwhile, I'm just going to start this. Okay, so first, let me just separate all the intervals. So let me see. X is strictly less than negative 1. So that will be this interval here, right? And the next one is x is between negative 1 and 4, but negative 1 is not included. Again, so you're going to have a open here, and then all the way up to 4, and 4 is also excluded. So you have this going on here. All right, and then the last one is x is greater or equal to 4. So in this case, we're going to have a closed or bracket and then all the way towards infinity. All right, so those are the three intervals. Now let's graph. So let's go with f of x equals to x cubed. So you got x and then y equals to x cubed. Okay, so where should we begin the x value? X value negative 1, and then like maybe negative 2, negative 3. I think that's good enough. Okay, so you're going to have y value is negative 1 cubed, so which is negative 1, negative 2 cubed, which is negative 8, and then negative 3 cubed is, what is that? Negative 27. Okay, so let me just jot that out. So when x is negative 1, y is negative, I should not put a closed dot right there. It should be open. All right, and then when x equals to -2, y is -8. And then when x is -3, your y is, oh goodness, all the way down to -27. So I'm just going to put it like, pretend like right there. So it looks like our graph is going to go, oh goodness, something like that. Okay, so let me just, it's not a straight line, by the way. X cubed, y equals to x cubed actually looks like this. Okay, so I'm only taking the tail piece of it, so it looks kind of straight, but it really isn't. Okay, so please keep that in mind. My gosh, that is the ugliest graph ever. But okay, I'm gonna go with it. All right, so now let's go with the next one. Y equals to 2. So again, we got a constant function on the interval from -1 to 4. So you're gonna have y equals to 2. So this is open. Is that y equals to 2? Yeah. And then all the way down to 4, which is here. And then it's still going to be open. Okay, so this is the graph of, oh my gosh, y equals to 2. I'll just write that out right now, y equals to 2, and this was y equals to x cubed. Okay, so now the last one is square root of x. So let's go with x. Y equals the square root of x. I'm going to pick some nice number here if I can. So starting point is 4. So the square root of 4 is 2, right? And then what would be the next nice number to compute? Maybe x equals to 9. All right, so x equals to 9. You got a square root of 9, which is 3. And the next one could be like 16. So square root of 16 is 4. Okay, so I think that's enough. By the way, square root of x function looks something like this. Okay, so this is the shape of y equals the square root of x. Okay, so let's do it. So when x is 4, y value is going to be 2, and it's included. So I don't know. I'm going to overlap it here. So here you go. That's the closed dot. Okay, and when x is 9, y is 3. And then when x is 16, your y is going to be 4. So there you go. I'll just mark it like that. Okay, so it looks like, again, this is not a straight line. Please note that. So this is y equals to square root of x. All right, so this is like the ugliest graph ever, but that's all right. Okay, so now, so that was part A. The whole entire graph is our f of x. Okay, so now let's go with part B. Find f of -5, f of -1, f of 3, f of 4, and 9. All right, so let's first go with f of -5. Okay, so when x equals to -5, right, your function defined there is y equals to x cubed, isn't it? Okay, so in this case, I don't know where the graph's gonna go because this graph is like the most ugliest graph ever, but you can still compute the y value because remember, f of -5 means when x is -5, what is the corresponding y value, right? So plug it in, -5 in place of x to compute your y value. Okay, so if I do that, then what do we get here? So our, when x is, let me just write it as f of -5 is same thing as -5 cubed, which is going to be -5 times 5 is 25, 25 times 1, 25. Oh my goodness. So this is going to go way down here. Okay, but anyways, our f of -5 is going to be -125. All right, next, let's go with f of -1. So when x is -1, okay, so we got two things going on here. When x is -1, here is one of the y starting point, and then this is another y starting point, correct? Okay, but remember, they both have open circles. That means what? Your function is not defined at that point. So when x is -1, your y is undefined for the top graph, which is y equals to 2. And then also, unfortunately, when x is negative 1, for the second graph, or where y equals to x cubed, your function is still not defined because it's not filled in. So in this case, f of negative 1 does not exist. Okay, so we meaning at x equals to negative 1, your y value is not there. All right, so I'm just going to write it as does not exist. D and E means does not exist. All right, so now let's go with f of 3. Okay, so when y equals to 3, so you got 1, 2, 3. What's the corresponding y value? Is 2. Okay, so I'm going to write that as 2. Let's go with f of 4. We got this. So f of 4 is here, right? So when x is 4, what is the corresponding y value? Well, we got two graphs going on, but at y equals to 2, your function's not defined, right? Because you have an open circle at x equals to 4, right? But the thing is, let's look at the y equals the square root of x. That guy is defined at x equals to 4. And in fact, the corresponding y value is going to be 2. All right, so I'm just going to write that as 2. So far, so good. All right, one more. We got this. F of 9. F of 9. All right, ready? So here's my 9. Here's my f of 9. Okay, so in this case, it turned out nicely, right? But if you didn't know what the value is, all you have to do is, remember, this is asking you when x is 9, what's the corresponding y value? So when x is 9, what's the corresponding y value? That would be 3. All right, so this portion is going to be 3. Phew! We did it! Okay, so if you sat through this whole entire lecture video, you are one tough person. That's all I have to say. So great job, everyone. And if you have any questions at all, you know where to reach me. All right, I'll talk to you soon.